In this lesson, we're going to pull together everything that we've learned about polynomial functions in order to graph the general shape of a polynomial function. So the three things that we need to know in order to graph the general shape of a polynomial function are things that we've already covered and looked at in previous lessons. First thing we need to know is we need to know the end behavior. The end behavior of a polynomial is the first thing we need to know. Second thing we need to know the zeros or the roots of the polynomial functions, or the polynomial function. Lastly, we need to know the multiplicity of the zeros or roots. So three things that we've already learned. How do we tie these together to graph the general shape of a polynomial? Well, let's go through this first example here and find those three pieces of information. Let's start with end behavior. We know that the end behavior of this is determined by looking at the term with the largest exponent value. That's this term right here. Since the exponent is odd, it's a 3, the exponent is odd, we know that it's opposite, so it's either going to go up to down or down to up. Because it's a negative coefficient in front of the x cubed term, or in the x cubed term, we know that it's going to behave like a negative slope, so that would be up to down. So we know our end behavior is up to down, looking left to right. So we know we start up, it's going to do some funky things in the middle and then end down. Question is, what's happening in the middle? That's where the other two pieces of information come in. So let's find the zeros of the polynomial function. To find zeros, we plug 0 in for f of x. So 0 equals negative 3x cubed plus 9x squared plus 12x. I need to factor this in order to find the zeros of it. I first see that every term has a negative 3x that I can factor out of it. Factoring negative 3x out of the first term leaves x squared. Factoring negative 3x out of the second term, if I'm factoring a negative out of a positive, it ends up leaving a negative, so that's going to be negative 3x. And then same true here is going to be a negative 4 if I factor a negative 3x out of 12x. Great, so we've factored out our greatest common divisor of each term, the negative 3x. I'm now left with a quadratic in the parentheses. So I'm going to factor that real quickly. I'm going to do a 1 and a 1 for the 1 in front of x squared. And I'm going to do negative 4, 1 as the two multiples, or two factors that multiply to negative 4. It produces negative 4 and 1, which indeed does add to negative 3, which is what we needed. So we know we pair up diagonals. So we end up with 0 is equal to negative 3x is the factor out front times two factors here, x plus 1 and x minus 4. There's many ways to factor this, however you need to factor it. Go for it. But these are the two factors that quadratic produces. So we now have our polynomial fully factored. I'm going to look at each factor separately and determine the value that makes it equal to 0. Looking at the negative 3x, I'm going to say that x equals 0 in order to make that 0. Looking at the x plus 1, I know that x equaling negative 1 will make that factor 0. Looking at the x minus 4, I know that x equaling positive 4 will make this factor equal 0. So these are the three zeros of my polynomial. Now, is that the number of zeros that we expected to get? Well, with a degree of 3, yes, we did expect to get 3 zeros, and there they are. The last thing we needed to find out was the multiplicity of the zeros. Because all of them came from roots that only have one multiple of that, or factors that only have one multiple of that factor, all of these have multiplicity 1. So there's nothing unique about the multiplicities of these zeros. So how do we pull this all together? Well, whether we saw it or not at the beginning, the past couple weeks as we've been solving polynomial equations, okay, we've been terming it as finding the zeros. Well, to find the zero of a polynomial, you plug 0 in for f of x. All along, you've been plugging 0 in for y. Now, how do you find your x-intercepts? By plugging 0 in for y. So whether we realized it or not, all along when we've been finding our zeros, the values that we've been getting are our x-intercepts. So coming over to my graph, I know my graph crosses at 0, I know my graph crosses at -1, and I know my graph crosses at +4. So by finding the zeros, you have found your x-intercepts. Combining that with what we already know about end behavior, where we start up and end down, can I start up and with a smooth curve travel through all of my x-intercepts and end down? It would look something like this. Smooth curve coming down. I've got to go through that x-intercept. I've got to turn around to come back through my second x-intercept of 0, and then I've got to turn around again to come through my final x-intercept of 4, and I end down. So I was able to use my end behavior of up to down and draw a smooth curve that goes through my 3 x-intercepts. So this right here is the general shape of what that polynomial looks like when graphed. Now, in all reality, it could be much shallower or it could be much steeper, but we do know that we have the right end behavior and our graph is going through the correct x-intercepts because our x-intercepts are our zeros. So let's do it again on another example right here. Because this one's going to have a little bit of a intricacy thrown into it that changes a few things. So, first thing we need to find in order to graph the general shape of this polynomial is the end behavior. Well, we know we look at the term with the largest exponent value. That's 2x to the 4th. Because my power is 4, I know that I know that both sides will look the same. It's either going to be up, up, or down, down. Because the value of my coefficient in front of the x is positive, I know that my end behavior is going to be up, up. Okay, next step is to find the zeros. That means plug 0 in for f of x. So 0 equals 2x to the 4th minus 32x squared. Great. Now, factor. We need to find the zeros, so we find that by factoring this. I see that every term has the greatest common factor of 2x squared. So I'm going to factor a 2x squared out of both terms. That leaves x squared in the first term and a minus 16 in the second term. Okay. I see that I have a quadratic with the middle term missing left in my parentheses, but what I also see is that what I have in the parentheses is actually the difference of 2 squares. We've looked at the formula for factoring the difference of 2 squares, and we know that it ends up being the first piece plus the second piece, and the first piece minus the second piece. So x squared minus 4 squared factors to x plus 4 times x minus 4. So our polynomial is now fully factored out. So we can ask ourselves, by looking at each term, what are my zeros? So looking at this first factor, looking at the first factor of 2x squared, what makes that equal 0? Well, x equaling 0. However, the x has a square on it. That means that really this is x times x, which means there's 2 locations that I could plug 0 in to make that 0. So we would say that this has a multiplicity of 2. Okay, looking at our second factor, what do I need to plug in for x to make that 0? Well, -4, because -4 plus 4 will give me 0. And last but not least, the x minus 4 factor, I need to plug in x equals 4, so that I get 4 minus 4 equaling 0. And so we know our end behavior, we know our zeros, and we know their multiplicity. And in this case, one of our zeros has a multiplicity of 2. Now we remember that our zeros are the x-intercepts. So I know that I cross through at -4, 0, and +4. So those are locations that I know I cross through, and I know that I start up and I end up. Okay? So can I connect a smooth curve starting up on the left-hand side, coming through my first x-intercept? I've got to turn around to come through my second intercept, and turn around again to come through my final x-intercept. Well, hopefully you're seeing the problem here. If I go through each of those x-intercepts, I'm ending up down, but my end behavior says I should be ending up. Well, the reason that it's working out that way is because of this 0 here of x equals 0. It has a multiplicity of 2. So believe it or not, we treat that a little bit differently when we graph. Okay? When we graph a polynomial where one of the x-intercepts has a multiplicity that is even, so a multiplicity of 2, 4, 6, 8, 10, so on and so forth, we actually don't cross through at that point. So at 0, we don't cross through. At 0, we only touch and bounce away. So what this would actually look like, okay, is starting up, as we know, coming through our first x-intercept, but we know that 0 has a multiplicity of 2, which means I come up to 0 and I bounce off of 0. It comes up and touches it and bounces away. An even multiplicity means I don't go through, I just touch and bounce away, which leaves me to turn around and come back through my final, and look at that, we end up. So we are able to achieve our end behavior because of the reality that that x-intercept of 0 has a multiplicity of 2, therefore it just touches rather than goes through. So there's two examples about how to graph the general shape of a polynomial function. The key pieces are, do we achieve the correct end behavior, and also do we travel through or touch and bounce off the appropriate x-intercepts.